Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS131, where we are discussing graph theory, chapter 10. And so far, we've discussed a lot of things about graph theory. We've discussed about graphs and graph models. We've discussed about graph terminology and special types of graphs. We've discussed representing graphs and graph isomorphism, which is one application of how graphs are represented. We have discussed about connectivity and how connected graphs can be found, right? So that is what we think is kind of like the main or the basic topics of graphs, where I've introduced the basic concepts of graphs, and then we moved on to different applications of graphs. So, for example, we discussed about the importance of Hamilton circuits and Hamilton paths. We then discussed about Euler circuits and Euler paths, and some particular properties that a graph must have to satisfy at least the Euler path or Euler circuits, although the same cannot be true for Hamilton paths or Hamilton circuits. Then we talked about shortest path problems. In particular, I mentioned Dijkstra's algorithm, which is a very critical part of traversing a graph and finding some certain properties in a graph for weighted graphs. And I think you might be studying them in a lot more detail, maybe in your data structures course as well, and probably applying them or even coming up with implementations for them for data structures when you'll be doing in your third semester. So so far, let's talk about the shortest path problem, and we have discussed that in detail, right? So let's now talk about planar graphs. And what are planar graphs? So planar graphs are any graph that can be drawn in a plane, in a 2D plane, without the lines intersecting with each other. And although it seems a very simple task, yet we'll notice how tough it is to draw a planar graph and to determine if a graph is planar or not. So let's begin this with the slides. And so now we're going to talk about planar graphs, and planar graph is basically chapter 10. Section 10.7 of your book. And in planar graphs, a graph is called planar if it can be drawn in the plane without its edge crossing, where a crossing of edges is the intersection of the lines or arcs representing them at a point other than their common endpoint. So for example, this one, we can notice that these two lines are intersecting with each other. This is the original graph. However, this can be easily drawn like this, where you take up this line, so you cross this line, and I'll use a pen here to highlight. So yeah, so you take up this point, this line, and instead of drawing it like this, you actually draw it like this. And this gives you this graph. And in this graph, we note that no line is crossing any other line, and this is a planar graph. So this graph is planar because it can be drawn into a representation where no line is crossing each other. So such a drawing where you can basically draw a planar graph into its planar version is what we call the planar representation of the graph. So this is the planar representation of the same graph. Similarly, if you take a cube, and in a cube we can notice that a couple of lines are intersecting with each other. However, you can actually draw it like this. By drawing it like this, you have basically removed all the line intersections, and this is a planar representation of a cube. So this graph here is the planar representation of the cube. And this is a cube. A cube is also a planar graph. This is what we mean to show. So a graph can be planar even if it is usually drawn with crossings, because it may be possible to draw it in a different way without crossings. And that is the challenge here. That given a graph, given a drawing may not be a drawing of a graph, may be a non-planar representation, and a planar representation of that particular graph may still exist. So what seems like a non-planar graph at first sight may actually be a planar graph, right? So the next question is that a planar representation of a graph splits the plane into regions, including an unbounded region. So for example, if we have this graph, we notice that there are different regions. 1, 2. A region is where basically this is like a completely bounded area, right? And then you've got the unbounded area, which is the external part of the whole graph. So in this case, in this graph, you have got 6 regions, starting from this is the first region, second region, third region, fourth region, fifth region, and finally your sixth region, right? So 5 are bounded in here and 6 is the unbounded region. So for instance, the planar representation of the graph splits the plane into 6 regions. In this particular case, this graph, the planar representation will split into 6 regions. And these are labeled in the figure for you. Euler basically showed that all planar representations of a graph split the plane into the same number of regions. So all planar representations of a graph will split the plane into the same number of regions regardless of how you plot it or how you draw it. If it is a planar representation, then each of the planar representation will split the graph into the same number of regions. So for example, what is a planar graph? Can you draw a planar graph for this K33 bipartite graph, right? So this is a K33 bipartite graph, as you might know. And the idea here is actually, well, this one cannot be converted into whatever you do. This one cannot be converted into a planar graph, right? And we'll know why in a couple of minutes. So we can show that a graph is planar by displaying a planar representation. Of course, a graph is planar if we can come up with a planar representation. However, it is much harder to show that a graph is non-planar because you might be showing a particular representation. Like it is like it exists for some, but you either have to show each and every representation, which is not possible, or to prove that the graph is non-planar, or you might have, if you don't show each and every representation, then you might have missed the ones that are planar. However, to show that if a graph is planar or not, to show that a graph is planar is really easy because you just need to draw the planar representation. So for example, let's take the same example. Is K33 planar? Is this graph planar, right? The idea would be to draw the planar representation and get rid of it. However, any attempt to draw K33 in the plane with no edges crossing is doomed. It cannot happen. It cannot work. You can try that. And you cannot actually change any lines here. Whatever you do, you'll not be able to avoid the line crossing. So K33 is not planar. So in any planar representation of K33, the vertices V1 and V2 must be connected to both V4 and V5, right? So the vertices V1 and V2 must be connected to V4 and V5. And these 4 edges form a closed curve, right? Of course, this one and this one, a closed curve that splits the plane into 2 regions, R1 and R2. And if we take this, V1, V5, V2, V4, this forms a closed curve and it splits in 2 regions, R1 and R2. The vertex V3, so let's call this R2 and R1, right? So the V1, V4, V2, V5 is R2 and R1 is the region that is outside it. And on the other hand, the vertex V3, if you add V3, that is in either the region 2, in this case it divided into region 2.1 and R22 and region 1 again, right? And at the inside, or basically it goes to the outside in R1, and in that case it's going to divide it into R11 and R12. So when V3 is in R2, V3 is inside R2, it is placed in here. The inside of the closed curve, the edges between V3 and V4 and between V3 and V5 separate R2. So the edges here will separate R2 into 2 subregions, R21 and R22, as shown over here. Note that there is no way to place the final vertex V6. So the final vertex V6 is the problematic one, because wherever you place it, so if you can place one vertex, K23, it works fine, like this. However, if you put in a K33, the third vertex, V6, it cannot be connected in any way with the other 2 vertices, with the other 3 vertices without a line crossing. So for example, if V6 is in R1, you put V6 in R1, then the edge between V6 and V3, the one inside V3, cannot be connected. It cannot be drawn without a crossing. If V6 is in R21, so you put V6 in R21, then the edge between V2 and V6 cannot be drawn without a crossing. And hence, on the other hand, if you put V6 in R22 over here, then an edge between V1 and V6 will not be drawn without a crossing. And since it's not possible, there are only 3 regions that are in here, and you're putting a vertex in one of these regions, but are unable to find the line without a crossing. Hence, it's impossible for K33 to be planar. So similarly, a similar argument can be used when V3 is in R1. So if you put V3 in R1, a similar argument can be used for the same thing. So it basically follows from this whole statement that K33 is not planar. This is something that you can always take in as a taken. So with K3, you just add find a closed path, right, first, and then from that closed path add the two missing vertices. So from v1, v2, v4 and v5 we added the missing vertices v3 and v6, and we found that it was not possible to get all the edges allocated with them without getting a crossing, even if you put v3 or v4 in any of the regions. And that's the proof of it. So K33 is non-planar. That is what you should know by hand. The different multiple applications of planar graphs, for example, planarity of graph plays an important role in the design of electronic circuits in automated tools, because the wires cannot cross each other in a circuit, and you want to keep them separate and you want to keep them safe. So for that reason, sometimes it's not possible to or in a drawing it would be very hard to read a drawing, a design of an electronic circuit, if there were a lot of lines that are crossing each other. So we can model a circuit with a graph by representing components of the circuit by vertices and connections between them by using edges. We can print a circuit on a single board with no connections crossing if the graph representing the circuit is planar. Yeah, so of course, if it's planar, then there's nothing crossing. When this graph is not planar, we must turn to more expensive options. For example, we can partition the vertices in the graph representing the circuit into planar subgraphs. We then construct the circuit using multiple layers, and each layer represents a planar graph, which is really expensive as well. Or we can construct the circuit using insulated wires whenever connection crosses. In this case, drawing the graph with the fewest possible crossings is important, and use of insulated wires is something that is generally discouraged. But if it's not possible to draw it, then to design the circuit, then we should use a minimum number of possible crossings. So the planarity of graph is also useful in the design of road networks. So suppose that we want to connect a group of cities by roads, and we can model a road network connecting these cities using a simple graph with vertices representing the cities and edges representing the highways connecting them. And we can build this road network without using underpass or overpass if the resulting graph is planar. However, if you have to use if it is not possible to draw a planar graph, then in that case you'll have to use underpasses and overpasses, overhead bridges, etc. And that the cost of the overhead bridges and overhead passes is a lot, so that's why we want to avoid those particular structures wherever possible. So if the planar representation is possible, we'd want to use it to build the road network. Now, what is the Euler formula that I talked about earlier? The Euler formula is simple. So let G be a graph with a let G be a simple graph that is connected in planar with E edges and V vertices. So let R be the number of regions in a planar representation of G. So let R be the let us get the planar representation, and let R be the number of regions in it. Then R, that is the number of regions in a planar graph, are always equal to the number of edges minus the number of vertices plus 2. So for example, the number of edges here, let's talk about, let's see the number of vertices here. The number of vertices here are 7, right? 1, 2, 3, 4, 5, 6, 7. 7 vertices. The number of edges here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So 7 and 11 vertices. And if you want to talk about the number of regions that are present in here, so the number of edges here are 11. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges, 7 vertices, right? So the number of regions are going to be 11 minus 7. 11 minus 7 plus 2, 9. So there are possibly 9 different regions in here. And if we go about it, we can basically say that 1, 2, 3, 4, 5, 6. Okay, are we having 6 regions? E minus 11 minus 7, 4 plus 2 gives us 6 regions, and that is the exact number of regions that we get. Yeah, so it's 11 minus 7, 4 plus 2, 6. In total, this one will have 6 regions according to the Euler's formula. And the Euler's formula is really simple, that in the sense that it only uses the I can't get the right thing here. Okay. So it's really simple in the sense that it uses the R is equal to E minus V plus 2. It just uses this formula to determine the number of regions. So you just need to count the number of edges, the number of vertices, and if this is a planar representation, means that no line is crossing another line. There's no intersection here. In that case, the number of regions are simply given by the number of edges minus the number of vertices plus 2 to get the number of regions. So suppose that a connected planar graph has 20 vertices and each of degree 3. Into how many regions does a representation of this planar graph split the plane? So if you have a planar graph, each planar has a simple number of vertices are 20, each has degree 3. So the number of edges in this are going to be 60, right? So 60 minus 20 plus 2 is the answer. As the number of regions it can be splitted if it's the planar representation. And we know that the graph is connected and a planar simple graph. So it will have 60 minus 20, which is basically, if you know, the number of edges in a graph are basically degrees, twice the number of, so the degree of a graph, sum of all the degrees is twice the number of edges. So the number of edges in the graph are then 30. And 30 minus 20 plus 2 gives you 10, plus 2, 12. So it will split into 12 different planes. And we'll see this in the example here. Okay, so this graph has 20 vertices, each of degree 3. So V is equal to 20. Because the sum of the degrees of the vertices, 3V is equal to 3 into 20, 60 is equal to twice the number of edges, 2E. Hence, the number of edges is 30. So 20 vertices, 30 edges. And then we simply put in the formula 30 minus 20 plus 2 is equal to 12. And this is the exact answer that I also got using the same formula and the same theorem here, twice the number of edges to get to the answer here. So if G is a connected planar simple graph with E edges and V vertices, where V is greater than or equal to 3, then E is less than or equal to 3V minus 6. So this is just a corollary that we can say that if the number of vertices is greater than or equal to 3, then the number of edges is strictly less than or equal to 3 times the vertices minus 6. And this comes from the same thing that the degree, the number of vertices, whenever they increase, it cannot be more than this particular 3 times the number of vertices minus 6 for the edges. And it's just a corollary. I don't need to prove it for now. We can kind of keep it in mind and apply it. This is true for each connected planar simple graph, right? Similarly, another thing that we can gain from this particular prospect is if G is a connected planar simple graph, then G has a vertex of degree not exceeding 5. So this is another thing. If G has a vertex of degree exceeding 5, then it may not be a connected planar simple graph. And that brings us to the next topic, which is degree of a region, right? So what is degree of a region? You know, a degree of a vertex already is the number of edges that are incident with the vertex. That's what we call degree of a vertex. And then we had in degree and out degree for directed graphs. However, for an undirected graph, the degree of a region is defined to be the number of edges on the boundary of this region. So for example, for this particular graph, we noticed that the number of edges for R1 are 3, 1, 2, and 3. For this inner region R2, it is basically 1, 2, 3, 4, 5, right? So the number of edges here are 1, 2, 3, 4, and 5. And also if you go from this part, so this is 6 now, right? So I can see this edge from here and also from here. On these ones, these are like the incident part is only 4 from here and 1 from here and 1 from here. So R2 is 6. Let's talk about the outer region, which is R3. In that case, 1, 2, 3, 4, 5, 6, and 7. And hence the answer for R3 is 7. Notice that it's a number of edges on the boundary. So whichever is if this is my edge, then and it's an open edge, then it's basically this boundary as well as this boundary that I can access. So since it's the boundary, it is the number of edges that I'm touching around. And in this case, I'm touching 6 because this is 2, and then we've got 4. And in the outer case, this is basically all the outer ones. These are 5, and then this one I'm touching the both boundaries. So this is equal to 7. So when an edge occurs twice on the boundary, so that it is traced out twice when the boundary is traced out, it contributes 2 to the degree. And that's why this one is contributing 2 and this one is contributing 2 as well. And we denote the degree of a region R by deg R. So degree of a region, degree of a vertex is two different concepts. The degrees of the region of the graph are displayed in the figure for you, and I've already mapped it out. So if a connected planar simple graph has E edges and V vertices with V is greater than or equal to 3, number of vertices are greater than or equal to 3, and no circuits of length 3, so it should not contain a circuit of length 3, then edges is basically less than or equal to 2 times the number of vertices minus 4. Then there's another topic that is, I'm going to kind of give you the brief outline of this, but this is not a very important topic, and I might, I'm not going to ask you about this in the exam. So this is just something for your information and for completing up this particular topic. If a graph is planar, so will be any graph obtained by removing an edge UV. If you remove an edge UV and add a new vertex W together with edges UW and WV. So if you add a new vertex and you can connect that vertex to the original vertices U and V. If you remove an edge, add a new vertex and add 2 new edges, such an operation is what we call an elementary subdivision. So you have divided the vertex UV into UWV, and you just connected U with W and V with W, right? And this is going to result in another planar graph. So the planarity is not lost if you divide a vertex, an edge, into basically 2 different edges using a new vertex, and that is possible through elementary subdivision. So the graphs G1 is equal to V1 E1 and graphs G2 V2 E2 are called homeomorphic if they can be obtained from the same graph by a sequence of elementary subdivisions. So you can combine some vertices, and if by combining them you can actually get the other graph out, then in that case such a operation is what we call elementary subdivision. And if you can obtain the second graph by using this set of or a sequence of elementary subdivisions, that is what we call a homeomorphic graph. So for example, let's take the graph G1, let's take the graph G2, and let's take the graph G3, right? So in this case, we can clearly say that A to C, we have put in a new point, we have used an elementary subdivision and added F, right? This one. Then in this line, we have actually performed 2 elementary subdivisions. So over here and over here, we have basically added 2 points, right? So this is the one G vertex, and now we have got an H vertex. And these 3 operations, these 3 elementary subdivisions will result in this particular graph. And you can already say actually that this is a non-planar representation, but we can convert it into a planar representation by simply flipping, maybe from C to B, we can have a line like that, and maybe remove this line altogether, right? And once you remove this line C to B, then you can actually have a point G over here and maybe H over here, in that case an F over here as well. So this is now a planar representation, and you have performed elementary subdivisions on it in a way that the planarity is being kept. And by this, so these 2 are what we call homomorphic graphs. G2 and G1 are homomorphic. The term homo means of the same type, and morphic means that they're morphs. Like isomorphic, it's the same thing. Iso, it means many faces. Homeo means same type with homo means same, homeo means something else actually, and morphic means faces again. So this is like the same graph actually with some elementary subdivisions that will result in the other graph ultimately. And here this is again the homeomorphic graph of this one, and we can actually see that this can also be the homeomorphic graph of this one as well. In this case, actually, we did not perform a particular thing here, but instead we performed on the edge BC, and on the edge BE, we got new points introduced, resulting in homeomorphic graphs. So the homeomorphic graph itself is very useful because it can be used in the Kuratowski's theorem, Kuratowski's theorem. And Kuratowski's theorem simply states that a graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. K5 is another graph, which is basically planar itself. We can see here that here. However, if a graph can be converted to K5, sorry, if a graph K5 is not sorry, a graph K5 is actually non-planar. So K5 or K33, the bipartite K33 graph is basically also non-planar, as we saw earlier, and K5 is another graph that is non-planar. So if you can convert a graph, if you can convert part of a graph into or show that the part of the graph is homeomorphic to K33 or K5, then by Kuratowski's theorem, the graph itself is non-planar. So in this case, for example, let's take this graph G. And if you notice that this particular path, we can basically merge them all together. This we can merge them together, and this we can merge them together to get a graph which is K5. And since this we can get by elementary subdivisions, we can get from K5 to this or from this to this. Hence, they are both homeomorphic. And since this graph is homeomorphic to K5, hence the graph is non-planar by Kuratowski's theorem. And it can work very well for K33 as well. So for that, I think you'll need to practice a little bit, you know, that how you can go from one graph to its homeomorphic representation. Although this is something that I don't intend to give you in the exam. This is a little bit of a tough question. And it's the same for this one. Again, we can convert this to K5 and show that this is also a non-planar graph. So let's take another example. In this example, is the following graph planar? Well, to answer that, you'll have to find, you can basically say that, does the graph contain this particular K33 notation in it? So we notice that with F, you have got F goes to A, F goes to H, F goes to I, right? So that's the representation. Then we can take up maybe D over here, right? So F and D are not connected, but D again goes to I, E, and C. And then you can maybe pick up J here, right? And J is doing the same thing. So since this graph contains this particular setting, hence this is also non-planar. And if we take this, well, we cannot find we'll always have some nice data crossing each other. Like this one can be homeomorphic to this one, and hence they are also non-planar. So then we move on to the last section, and I'm going to go quickly through it in the same lecture. Actually, instead of putting it in a different lecture, I'll put it in the same lecture, and that is the topic of graph coloring. And the reason we are having graph coloring is because we just want to get introduced to the idea of graph coloring and graph in graph theory. We'll probably study this in much more detail in some of the later topics. And I'm not going to talk about it in detail, but I'm just going to tell you that this is one of the most interesting and one of those topics which has had widespread applications, just like Hamilton paths and circuits and Euler paths and Euler circuits. So this is something again that is very interesting and very important. And we'll want to see the practical applications of graph coloring. So what is graph coloring? A coloring of a simple graph is the assignment of a color to each vertex of the graph so that no two adjacent vertices are assigned the same color. So if you have two vertices that are adjacent to each other, you will want to assign them different colors. And if that is possible, then that is one coloring of a simple graph, right? So if you can assign them colors so that different colors so that no two adjacent vertices are assigned the same colors, then in that case, that is one possible coloring of the simple graph. And why is coloring important? Well, you can assign any colors, of course. If you have got n vertices in your graph and you can assign them n colors, that is going to be one simple coloring. However, the basic idea is to find the chromatic number of a graph. And the chromatic number of a graph is simply defined as the least number of colors needed for coloring of this graph. So one coloring of this graph, the least number of colors that are required to color a graph is what we call the chromatic number of a graph. And the chromatic number of a graph G is noted by this particular symbol, right? So this represents the chromatic number of a graph G. So here's the theorem. The chromatic number of a planar graph is no greater than 4. So if we have a planar graph, right, the chromatic number will not be more than 4 for sure. So for example, in this one, which is a planar graph, the chromatic number has to be less than or equal to 4, but not greater than 4. And we can see that, for example, if we assign them different colors, we start with red, blue, and green. So 3 colors are necessary for this path. Then again, the same colors, blue, green, and red can be used for this one, blue, green, and red for this one, blue, green, and red for this one, blue, green, and red for this one, and finally blue, green, and red for this one. So the chromatic number of this graph is 3, again, not greater than 4. And we know that you can actually look at this graph as well. So this is also a planar graph. And in this case, if you can assign colors to it, again, you can basically use 4 colors now, since red, green, and blue. And finally, you've got a brown there for this one. Again, not more than 4. And this is planar as well. So what about complete and bipartite graphs? Well, for a complete graph, as many are the number of nodes, the same number of colors are required. So for example, for a K5, we require 5 different colors, and we know that this is a non-planar graph. Similarly, K3-4 will strictly require the same number of colors as 4. So in this case, we note that you can assign, for a bipartite graph, actually, you only need to assign 2 colors. And it's true for a complete bipartite graph because you can divide it into 2 different portions, and both of the portions, and there's no connectivity between any vertex within the portion. So we have assigned the first partition as red color and the second partition as blue. And we note that this works absolutely fine since no adjacent vertices has the same color. However, for a complete one, since every vertex is connected to every other vertex, we need as many colors as the number of vertices. For a complete bipartite graph, we actually require only 2 vertices. So let's talk about cycles then. For a cycle, possibly we might require 2 to 3 colors. For example, for C6, we require basically just 2 colors, one red and blue, red and blue, red and blue. However, for C5, we actually require 3 different colors, red, blue, and yellow. And that is true because you can start assigning them colors. If you have odd number of vertices in a cycle, you'll basically need 3 colors. If you have even number of vertices in a cycle, you'll probably only need 2 different colors. So what are different applications of graph colorings? And let me tell you that this is again an NP-hard problem. To determine the chromatic number of a graph is an NP-hard problem. And this is something that I personally am working on getting it researched and solving it using deep learning. However, other methods may also be possible. There are many other heuristic methods to determine the graph coloring. I'm not going to talk about them in detail in this particular course because this is a very basic introductory course. However, if you're interested in finding more about how the problems in graph coloring are used, you can actually go and search for different road networks and applications of graph theory, and you'll probably find them in everywhere. In particular, in research, there are so many algorithms that have been designed specifically to find the chromatic number, and a lot of papers have been published in this regard in the past few decades. So scheduling of final exams of universities such that no student has 2 exams at the same time. I think this is one application that you guys can even make up to schedule our final exams in a way that you can come with a software for GIK, because no student takes more than 6 courses. So the chromatic number of this would be close to 6. And by determining the right chromatic number, actually, you can come up with the scheduling of final exams of the university in a manner that no student has any clash or 2 exams at the same time. Similarly, frequency assignment to different radio channels, because whenever a new radio channel is launched, you don't want to have its frequency matched with another one in a particular region. Within a given area, you would want them all to have a different frequency. And that would be possible if you can use a graph coloring algorithm. Similarly, assigning index registers to the most frequently used variables instead of regular memory in a compiler application is another application. You're not going to study compilers probably, not as a course at least. You have studied compilers in C++. You have a bit of an idea of what a compiler is or what it does, really, more than what it is. You know what it does. If you can assign index registers to the most frequently used variables, the index registers are much faster to access than the regular memory. So it's even faster than the regular memory. So if a variable is being accessed a lot of times, you can actually use a graph coloring algorithm to come up with identifying the index registers, identifying the most frequently used variables to give them the index registers. That is the aim of this particular thing. So again, another application from a totally different field, but a very valid and a very useful one. So that is the end of chapter 10, and some of the topics that we have discussed in quite a lot of detail. Like I said, I'll kind of go through a quick summary now. So we started off with what are graphs and graph models. We discussed graph terminology and special types of graphs. So that was the very basic things. Then we discussed how we can represent graphs in terms of adjacency lists and adjacency matrices, as well as incidence matrices. And then we applied them to the concept of graph isomorphism, different graphs that are that have the same structure, let's say, or same face, and we then wanted one-to-one vertex mapping, at least as a result from isomorphism, or you could actually give me the adjacency metrics for both the graphs, which are isomorphic. Anyway, that was up till section 10.3, I guess. Then we moved on to chapter 10.4, where we talked about, again, some form of basics about connectivity. So how is a graph connected, strongly connected components, weakly connected components, and a bit about the definitions again. So this was, again, introduction part. So after graph isomorphism, we moved on to some more introduction here in connectivity regarding connections. Then we moved on to the new topics or applied topics of this particular course or section, let's say, chapter 10, graph theory, where we talked about section 10.5 was all about Hamiltonian and Euler paths. And I think the next thing was more about, after I talked about Hamiltonian circuits and Hamiltonian paths and Euler circuits and Euler paths, the main thing there was that in Euler circuits and Euler paths, we wanted to traverse each and every edge of the graph exactly once. And there are some theorems like based on the degree of the vertices, which basically states that you can find an Euler path or an Euler circuit if there are, for example, all vertices are of degree even, number one, or if all vertices are of degree if there are exactly two vertices of odd degree, even then you can find an Euler path between them, but not Euler vertex. So those were the two main theorems, and it was very easy to find an Euler circuit basically by using an algorithm that we saw. Then we moved on to the next topic, which was based on Hamiltonian circuits and Hamiltonian paths. And again, there the topic was quite simple, I would say. The idea was that we want to traverse each vertex exactly once, although the number of edges we might skip some, or we might not visit some. And the idea is that we basically, although the problem seemed very similar to Euler paths and Euler circuits, yet it's not so simple. And actually the algorithms that do exist for finding Hamiltonian paths and circuits are basically in exponential time complexity, and hence we cannot use them for computing them even for a moderate amount of data. And the idea here would be that there are some theorems here, like Dirac's theorem and Ore's theorem. However, those may be used to show maybe existence of Hamiltonian circuits, but again, determining the exact Hamiltonian circuit is an exponential problem and a work in progress in terms of research. So then we discussed about weighted graphs, and in particular, we discussed the shortest path problem. We discussed how to determine the shortest paths in a weighted graph, and in that we studied the Dijkstra's algorithm. And we applied that on one particular example, but you can actually apply this as algorithm on a lot of different examples and come up with solutions for it. I can basically say that determining the Euler path or Euler circuit, or maybe the Dijkstra's algorithm, application of Dijkstra's algorithm, is one of the favorite topics from this particular section. And then we can actually move on to the planar graphs. What is a planar graph? The definition is really simple: a graph that basically divides a representation in which we can draw the graph in a single plane without lines crossing each other, except at their endpoints. and we basically wanted to see the planar representation of a graph. And of course, the graph then divides it into regions, and there was some certain theorems related to the regions, and I think that was a lot of information about planar graphs and regions, etc., in section 10.7. And finally moved on to section 10.8, which was about graph coloring. And we discussed what graph color is, what coloring of a graph is. And I showed you actually that, how different colorings, how many different colorings will exist for a complete graph, or a bipartite graph, and so on and so forth. So that is all about chapter 10, graph theory. We'll now concentrate on chapter 11, which is the minimum spanning trees. What is a tree? We'll discuss that. What is a minimum spanning tree? We'll discuss that in a bit of a detail, actually, as much detail as we saw for graphs. And then after that, I'll then move on to chapter 3, which is complexity of graphs. And I think then we're done with the whole course for discrete structures. It was a lot of fun teaching graph theory to you, and to explain the concepts of graph theory. You probably need to again view these examples quite seriously, and maybe apply them at the end of the book exercises that I'll basically send marked for you. And you can practice them on those examples, and you might find something similar, at least in the final exam. So with that, I wish you all the best to solve these problems, and I hope you have learned something about chapter 10, about graph theory, from me in these lectures. And of course, it was a lot of fun to teach graph theory to you. Let's see you in the next lecture on spanning trees. Till then, take care. Allah Hafiz.